All right, so section 9.4 are the comparison tests, and there's actually two types. We can directly compare a series to a known series, or we can do the limit comparison test. The direct comparison test is faster if there's a really clear inequality that we can define, but the limit comparison test is actually a little bit more robust, and it's kind of harder to mess up. So I personally try to use the limit comparison test wherever I can. And this is kind of the point where you're going to see where I was telling you guys, if you really get good at these infinite limits, limits become your best friend because the limit comparison test is quite useful. So when we're doing a comparison test, right, we want to take a series that may look kind of like a series we've worked with before, but there's always something extra weird in there that sort of violates the standard form. So what we want to do is we want to compare that to a series that we think might behave the same way. So one of the things you want to make sure we're looking for, right? And we want to make sure we understand that these differences can be really subtle, okay? So if we're talking about known series, well, this is a geometric series. But if I write a series in this form, that n in the numerator violates the standard form of a geometric series. So this is not geometric, okay? But the only difference between these two series is I have a constant in the numerator on the one on the left, and I have a variable in the numerator on the one on the right. So chances are, because exponentials grow so quickly to infinity and the exponents in the denominator, these two series are probably going to behave in a similar manner. So if the guy on the left converges, I'd put money down to say the guy on the right probably will too, right? And so by either applying direct comparison or the limit comparison test, we can actually confirm that hypothesis, right? The other series we've been playing with a lot is p-series. So this is a p-series, right, where p equals 3. But if I had a +1 in the denominator, not a p-series anymore, okay? Now, if you look at the limits of these two terms as they go to infinity, we all know that as we get closer and closer to infinity, that +1 is going to be insignificant. So I could, probably logically say that the series on the right is going to behave almost identically to the series on the left as the values approach infinity. So the series on the right-hand column, we could compare back to these known series and probably say, well, these two things are probably going to converge, right? The other test we talked about was the integral test. So if I gave you something like this, this is easily integrated. You would do a u substitution. Your denominator would be u. Your du would be 2n, but since we have that extra n in the numerator, we can easily turn that n into 2n. So we could integrate this with not much difficulty just doing a straight up u sub. But if I tweaked this guy a little bit, and I square the n in the numerator, we can see this is not easily integrated. So all the series on the right, all the methods we've learned up till now would not work to evaluate any of them. So we have to have a new way of doing it, and the new way we're going to learn today is two types of comparison tests. So the first type of comparison we're going to do is called the direct comparison test. So there's some criteria that we have to have in order to apply it. So we need these terms to have we have two different series, and we need to be able to establish between the two series a well-defined inequality, all right? If it's true for all n, that's great, but just like we saw earlier when we looked at 1 over n and 1 over 2 to the n, if there's a point kind of early on in the series where one function overtakes the other one, right? The ones we looked at before, we saw that happened at the 4th term. So that capital N just stands for a constant value or a spot in the series where we know one of them overtakes. So then beyond that point as you go to infinity, we have a well-defined inequality. So if we can establish this relationship between the nth terms of any two series, there are two ways that you would use the direct comparison test. You're going to use it to prove something converges, or if you suspect something diverges, you can apply it there as well. So if the bigger series, B sub n, converges, then the smaller series converges. So I kind of like to use the Indiana Jones analogy for this. So you're in a room in a cave and the ceiling starts collapsing down on you, right? And if you get stuck in the room and the ceiling goes all the way to the floor, well, you're going to get squashed right along with it. So when we're trying to prove convergence, we're trying to prove that A sub n converges. And the way that you do that is you find a known series that is bigger than that series. And if you can prove that that converges, then you know the thing smaller than it has to collapse down to 0 as well and converge, right? So the big series traps the smaller series. It's trapped up underneath it. If you want to prove divergence, well, if the smaller series diverges, then the larger series must diverge as well. So the idea here is if we want to prove that B sub n converges, if I can find something smaller than that that's blowing up to infinity, well, then the thing bigger than that has to blow up to infinity as well because it's always greater than that, right? So what you want to make sure you're trying to do when you do the direct comparison test is, are you proving convergence? Then find the ceiling. Are you proving divergence? Then find something smaller than it that blows up. So some of these are quite obvious and easy, and some of these can be kind of subtle. So the direct comparison test, like I said, may not always be the way to go. You may want to jump to the limit comparison test instead. But let's look at an example of how this can be applied. So this looks like a geometric series. It's got that 3 to the n in the denominator, but that plus 2 makes it not geometric anymore. But I think, and I think it's kind of intuitive, that that's probably going to behave very similarly to 1 over 3 to the n as you get to infinity. So we would want to compare it to a series bigger than it. So if you remember, if you reduce a denominator, if you make a denominator smaller, it makes the whole fraction bigger. So we could set up an inequality where a sub n is 1 over 2 plus 3 to the n, and that should be less than or equal to 1 over 3 to the n for all n. And that's a geometric series. We actually know what that guy does. So B sub n converges, right? It's a geometric series. And since it's bigger than a sub n, that means the smaller thing converges too. And that's it. That's how you apply it, right? But the tricky part of doing this is establishing the inequality. So let's look at one where it's not quite so obvious how to set up the inequality. So this one kind of looks like a p-series where p is 1/2, and we know that would diverge, right? But once again, the +2 has ruined things for us. So if you try to just drop the 2, all right, what would end up happening is your inequality would look like this. Now, that is a known series that diverges, but all you would be doing here is showing I found something bigger than my series that diverges. That doesn't prove divergence. Well, of course things bigger than it might diverge, right? So I need to find something smaller and than this sequence to say that it diverged. So this diverging is actually inconclusive because the inequality is running the wrong way. So what is something that would be bigger, because I need the denominator to be larger so that the whole fraction gets smaller, but what is something that is bigger than the square root of n that I could put in the denominator that we also know would diverge? Think p-series. What's the biggest diverging p-series? 1/n. N is definitely bigger than the square root of n, right? And when p is 1, that is the largest, right, p-value that we can have for divergence. So what we can say now is 1/n is less than or equal to 2 plus the square root of n. This isn't true for all n, but it is for all n greater than or equal to 4. So only the first 4 terms it doesn't work out, but since we're only looking at things at infinity, everything past 4, it's a well-defined inequality. So now I have found a smaller diverging sequence, right? So the fact that this guy diverges means that this diverges too. So is there any questions about this? So conceptually, people usually don't have much trouble when they think about it for a minute, like grasping the concept of this test, that you need something big to trap something to show it's crashing down, right? You need something smaller to show that it's blowing up. It's setting up the inequality that's really a struggle for people. So you just want to be real careful and make sure that you're picking the correct series and you're setting up your inequality the best way. So you just want to verify that the thing is greater than or less than. Personally, I try to avoid this test unless I absolutely need it. It is literally the last test I use unless anything else, because it is so subtle and so hard to do, and I mess it up all the time. So, but in terms of list of priorities, I always put it at the bottom. Like you want to exhaust every other avenue before you kind of result to this test. Unless it's like the first example where there's just a really obvious inequality to set up, and then it's a really quick test to perform. All right. Any questions? No? All right. So let's look at the other type of comparison test. This one's my favorite. And this is the limit comparison test. So it's a little easier to perform. It's a little harder to mess up. And it's got really simple criteria. So what you need are 2 series with positive terms. And the limit, as n goes to infinity, of the a sub n term over the b sub n term, if that equals L, where L is finite and positive, then your two series either both diverge or they both converge. So you can use either one of these tests to prove convergence or divergence. And what's really kind of weird when you first start learning the limit comparison test is I could produce two series that both diverge, and we could evaluate the limit, and we would get, let's say, the answer 1. And that 1 would mean they both diverge. I could then give you two series that converge, set up the limit, and we would evaluate the limit and get 1, and that 1 would also mean both series converge. So one thing to keep in mind about both of these tests, you only really use them when you kind of already can see what's kind of the end game coming. So if you suspect, because when you're setting up the inequality for the direct comparison test, you kind of have to know which way to set up the inequality. You have to have an idea of what's going to happen in the series. Same thing is true here. You're going to get a series, A sub n, then you're going to have an idea of what's going to happen, so then you're going to compare it to a series B sub n that you think behaves the same way. If their infinite limit is finite, what that's telling you is they do behave the same way. So then the answer is whatever it compared to. If you compared it to something divergent and the limit came out to be 2, then they're both divergent. If you compared it to something convergent and the limit came out to be 1, 2, any real number, they're both convergent. So let's look at what this would look like in some examples. So let's do a really general case first. So I have a series 1 over an plus b, that is a times n plus b, where a and b are just positive constants. So what series do you think this thing might be behaving like? Always check the powers of n. One over n, right? That's n to the 1, right? So it's probably just a manipulation of the harmonic series. So we would compare this to one over n. Now, in order to run the test properly, I have to know what 1 over n does. And I know that this diverges. So this means if my limit I set up produces a real result, they're both going to diverge, right? So we set up the limit. So we have the limit of the first series divided by the limit of the second, but since it's a fraction, that's the same thing. We know we're just going to multiply times the reciprocal. And then you'll simplify your expression as best you can. And we end up with this. So what does that limit equal? 1 over a. Since we know a is a positive number, this is in fact a positive finite result. So both series diverge. Now what I love about this test is it doesn't really matter which thing you put on top and which thing you put on bottom. Right? With direct comparison, you had to build the inequality in a specific direction. But if I just flipped this, if I put 1 over n over 1 over an plus b, all it would do is flip this fraction right here, and the answer would come out to be a, which is also positive and finite. So I would come to the exact same conclusion no matter which one I put on top or bottom. So this test is a little bit more robust than the other tests. So let's look at some given sequences and kind of see if we can figure out what we should compare it to, because that's usually the most difficult part for people when they're performing this test. Okay, so let's look at the first sequence. So the denominator of this sequence just looks like a polynomial. And one thing we know about polynomials, when we look for their infinite limits, only the leading term is going to matter. Everything else gets dwarfed. So if you look at the highest power of n in that denominator, it's n squared. So I would compare this to the p-series 1 over n squared, because I think it's going to behave the same way as you get to infinity. This is a p-series, right, where p is 2, so that means it converges. So when you perform the limit, and I'm going to give you 3 of these, and I actually recommend at home you go home and set the limits up and evaluate them just to show which you get the correct answer. But when you perform this, you do get a real result, and you would say they both converge. And so what you're going to see when we finish this is that all the third column, whatever we decide is happening, matches what we suspected in the second column. It's the only way this test works. You kind of have to have an idea going into what's going on. So what should I compare this to? What's the highest power of n in the denominator? 1/2, right? It's under a square root. So we would compare this to 1 over the square root of n. That's a p-series where p is 1/2, so that means it diverges. And I suspect that the 3 and the 2 will not matter when you get to infinity. It's basically going to turn into 1 over the square root of n anyway. So when you perform the limit test on this, we get that both of these diverge. So now we have a polynomial on top of a polynomial, but the same thing's true, right? As we're going to infinity, only the leading terms are going to matter. So there's actually 2 ways you could think to compare this. The first series you could compare it to is, well, simply take the highest power of n in the numerator and the highest power of n in the denominator. I don't really like that way because it's not really obvious to me that, like, this is not a form of like a known series we like. Or you could take those highest powers, right, and then just simply simplify, because you can see that an n squared is going to cancel. So I would compare it to 1 over n cubed, because that's what's really going on. You have an n squared in the numerator, an n to the 5th in the denominator, and that's really just going to reduce down to the form of 1 over n cubed. But if you have trouble seeing that, you can always start here and simplify to get here. So this is in fact a p-series that converges. And when we perform the test, we will in fact conclude that they both converge. So the point here is you gotta know what's happening before you apply these tests, or at least have a reasonable suspicion of what's going to happen before you can apply these tests. So all the series in the first column look like some kind of manipulation of a p-series, right? So if you've got a polynomial, or essentially if you're dealing of powers of n, that is when the limit comparison test is really, really useful, and we're usually going to almost always compare them to p-series. All right, so let's look at a couple examples where we actually apply the test. So what should we compare this to? You have to do a little math with fractions, but 1 over n what? Not to the 4th. What's the power in the numerator? It's 1/2. What's the power in the denominator? 2. So what does that reduce down to? 1 over n to the 3/2, or 1.5, right? So you can cancel the 1/2 out of the numerator, cancel the 1/2 out of the denominator. So it's really, right, 1 over n to the 3/2. Because I can write that in squared as 4 over 2, and then when you subtract the 1/2, when you cancel, you'll get 3/2. So this is a p-series. This converges, right? So if you're using this test, you have to tell me what the series you're comparing it to does, right? So then we set up the limit. So it's the limit of the first thing, right? And then we divide by the second term, which means we're going to flip this fraction. And when I multiply into the 1/2 times into the 3/2, you add them together and get into the 4/2, which is just n squared. And the limit of this is 1. That is in fact greater than 0. So both series converge. Yes, I'll copy in. Okay, so let's look at another one. So the 2 to the n in the exponent isn't going to go anywhere, right? And the n in the numerator, if we kind of did a power reduction here, right? The n in the numerator is n to the 1. We have n squared or n cubed in the denominator. So really this is some form of like 2 to the n over something squared, right? And we know that an exponential is going to grow much, much faster than a polynomial. So I'm counting on this thing's probably going to diverge. The numerator is just blowing up too fast. This thing isn't going to reduce. So I'm going to compare it to 2 to the n over n squared, right? But I have to know what this does, and this isn't just a general form of a sequence. This is like a combination of an exponential and a power series. So what we would do here is we'd say, well, I need to demonstrate that this diverges before I can do the limit comparison test because I can't just say it, right? So we know that this is going to diverge because if you take the limit of its nth term, right, that is clearly infinity. And even if you did L'Hopital, you would do it twice, and you would see that the 2 to the n doesn't go anywhere, and the n squared will reduce to 1 after 2, or will reduce to a constant after 2 derivatives. So now I can set up my limit. Right, we're still taking the first term, dividing by the second term, so we'll multiply times its reciprocal. Right, I want to try to simplify this as much as possible, but right away the 2 to the n's cancel. And I end up with n cubed over 4n cubed plus 1. So what's that limit? 1/4. That is positive, right, and finite. So both series diverge. If I had done it upside down, right, this is like the 1/a example, if I'd done this upside down, the limit would have come out to be 4, which would have taken me to the same conclusion. That is finite and positive, so they both diverge. All right, so this is the end of this section. We finished a couple minutes early, so we'll start the quiz a little early. I have 5 extra minutes. It's only 2 problems. So just do me a favor, when you write it on your paper, write quiz 11 part 1. Because I messed up when I wrote I don't want to get all my numbering wrong because I've written some of them in advance. Let's open this guy. Fall 2017. Homework and quizzes. Quiz 11. Yeah, there we go. So for this first one, you're going to have to write the nth term and then see if you recognize the series and can test it for convergence. If it does converge, you should be able to sum it up and give me the sum. Oops, sorry. And remember, you've got conditions that have to be met before you can apply any of these formulas, so you need to make sure you check that things are the way they're supposed to be. But I'll be walking around, and then the other 2 problems are kind of more of integral tests. They're section 9.3, so we'll do those on Wednesday.